class. Okay, we're dealing with probability. And let me just review what we did last time, so you can sort of get an idea of what's just all the technical terms and how they're used. So we have a probability experiment. Let's call it a probability experiment. And what this is some activity in which there's defined specific outcomes. And so it's only the experiment only allows these specific outcomes to occur. Property practice. No, the property practice is not, it's the probability practice. I think just let's go back and make sure that there's property practice is down here. It's sort of there's probability exercises and probability programs at the top. We started this one last time and we'll continue with that today. And then we went through and ran some of these programs on Thonny as examples of probability experiments and what their outcomes were. Let's see. Okay, so Jillian, if you go to the resources page, and it's like if you go down under resources and exercises, you may need to refresh your screen. It could be that there's like a web cache issue, but if you refresh your screen, especially if you haven't turned your computer on and off, you just like suspended it. Okay. Good. Good. You have it now. Okay. So, so a probability experiment is something with defined outcomes. For example, is a coin toss in which the outcomes are coin lands heads up, coin lands tails up in the usual convention. So we give names to the outcomes. Like here, there's going to be, say, H and T for heads and tails. Okay, and then another example would be a dice roll in which you could have like a dice with different numbers of faces if it was different shapes and it was arranged right. So for example, the usual dice has the outcomes are the dice cube lands with one face up, and there's going to be a certain number of dots, like 1 dot or 2 dots, or however the 3 dots are arranged, and then 4 dots. So if it's a cube, and if it's a dice with 6 things, so we could label the names of the we usually choose names of the outcomes. So the names here could be just say 1, 2, 3, 4, 5, and 6. And so, I mean, you could choose an activity in which something certain happened. For example, it might be that if you had a heavily weighted coin, it would always roll and come up 6. There might be, so then, but that's okay. I mean, the value of probability is to deal with certainty and uncertainty, but certainty is just a special case of that. So we have these probability experiments are sort of paradigmatic ones. There's lots of other ones. For example, at the end of the last class we had, you can look at the sort of the experiment of having a set of n people, say where n could be 30 or 50 or 100 or 1,000, say, and asking for their birthdays, meaning the day of the year they're born, not the date. Okay, so here you could label them by the actual names, like January 1st, January 2nd, January 3rd, February 15th, September 20th, up through December 31st. But there's 365 days in the year, and so for the purposes of of doing this thing, you can see for each person, for one person, there's 365 possibilities. So the experiment could be, you go up to a person on the street, say, and ask them what their birthday was, and if they, if it was some context where this was a reasonable request, then you would they would identify it, and you would identify them as having one of these numbers. So since you don't know, I mean, they know that their birthday is certain, but you don't know what it is. So there's uncertainty in terms of knowledge. So sometimes the uncertainty that probably deals with is intrinsic, a coin toss or a dice roll, or it's just a lack of knowledge. This is sort of a lack of information uncertainty. Okay, and there's lots of other examples like this. These ones are especially important because and most things are sort of a mix of lack of information and intrinsic uncertainty. Okay, so now so those are probability experiments, and what we do is we build a mathematical model of these experiments, because these are things in the real world, and we build a model because each experiment has a set of defined outcomes. We define the sample space as the sample space is the set, so it's a set of all outcomes. Okay, so usually we sort of identify the set and talk about it in terms of the names of the outcomes. So we'll say the sample space for the coin toss was the two element set H and T, where this is the coin lands heads up, the coin lands tails up, and then we have the sample space for the dice, which we can label as, for the six-sided dice, as 1, 2, 3, 4, 5, 6. And then the, say, birthday problem for one person would be like, we could label it the numbers 1 through 365. So in fact, it's like a big dice with 365 sides. Okay, so we have this idea of the sample space. This is sort of a model or identifies the outcomes in some probability experiment. And then we have what we're going to be interested in is events. An event is a subset of sample space. So for the coin, the subsets of S equals H and T are the empty set, the set with just H, the set with just T, and S itself, the whole sample space. Okay, now the events with one outcome are called simple events. They're what you usually think of the outcome of experiments. You toss a coin, you get heads or tails. You roll a dice, you get 1, 2, 3, 4, 5, or 6. But there's other events. I mean, here that's all the events. There's this empty set, nothing happens. Heads is up, tails is up, and then the S is a compound event in which one of these two occurs. So for the dice roll, there's more subsets, right? There's the because there's 6 of them. Say, well, it's easier. It's going to be easier. Let's say we had a 3-sided dice. Well, that's sort of, yeah. Let's say we have a 3-sided dice. Well, that's just going to be the somehow we arrange that only one of 3 sides can be face up, and so the events are the subsets. Well, it's the empty set. Then there's the simple events. Those are the simple events. Okay. Then there's the events. There's going to be a bunch of events that are well, there's actually not going to be that many of them because there's going to be 3 of them, one with 1, 2, 1, 3, and 2, 3. And then there's going to be the whole set S with all 3. So here there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 events possible for this 3-sided dice. And there's up here, there's 4 events for the coin. So counting events is like counting subsets. So that when you go to larger spaces, there's a huge number of subsets. So that's anyway. So those are the idea of events, and events are the things that we attach probabilities to. So once we have events, we can choose a probability model. So a probability model is an assignment of a number P but for each event. Okay, but it has to satisfy, you know, such that say a number P to each event such that 1 P is greater than equal to 0, less than equal to 1. Okay, so it's a fraction. It's a positive fraction less than 1 or equal to 1. And the second requirement is that P, I think we're going to use a capital P. P of the empty set equals 0, and P of the whole set, the sample space, equals 1. And we sort of intuitively think of probability 0 as being never happening. And this event, 1, means always happens. And that's within the context of the probability experiment. So it's like we always have to get, if you tossed a coin and it somehow landed in a crack, that just isn't a probability experiment as defined, because we would just throw that out as a bad coin toss, and just consider those where the coin lands heads up or tails up. So that's why this sort of says, okay, we're only going to consider the outcomes identified for that probability experiment. So everything else is in between. Okay, but there's a third requirement. Well, there's actually more than there's the idea that if two events are mutually exclusive. Well, what does that mean? Mutually exclusive. So two events. So if A intersection B, if the two events A and B, the intersection of them is the null set, right? They're mutually exclusive. Then A and B are mutually exclusive. Well, that just so the words mutually exclusive just means that the two events have no outcomes in common. Because they have no outcomes in common, they cannot both occur at the same time. So, but that sort of raises the question: what does it mean for two events to both happen? Well, let me finish this story here about two events. If they're mutually exclusive, then that means that the intersection is zero. Then the probability of the union has to equal the probability of A plus the probability of B. Okay? One of the consequences of this is if you summed up all of the probabilities for the simple events, right? Because the sample space S equals simple event one. These are simple events. Say this is simple events. Simple event two, simple event three, up to simple event, say n. If the sample space has n elements, then, well, you can see the sample space then is the union. Well, okay, I didn't say this quite right. Because events are subsets. So the sample space is not a set of events. It's the outcome one, outcome. These are outcomes. Outcome one, outcome two, outcome three, up to outcome n. So for the coin, there'd be two. For the dice, there'd be six. For the birthday problem, there'd be 365. So if this is true, then S equals event one, union event two, union event three, union each of the simple events En. Okay, so it's the union of all the simple events because there's one event in each one. And these are mutually exclusive. So simple events are mutually exclusive. Because they're just one element in each one. So that means the probability of the sample space has to equal, according to this the probability of E1 plus the probability of E2 plus plus the probability of En. And since this equals 1, we have to have that the probability of the sum of all the simple events has to equal 1. And that's a strong constraint. For example, for the coin, right? The probability of S equals 1, which equals the probability of, say, heads plus the probability of tails. So if you make this 1/4, this has to be 3/4. If you make this 1/10, this has to be 9/10. So those would be different probability models. Now you might choose a probability model according to data to model some situation in the real world and try to understand it. So that is sort of the basic principles of the probability, sort of what defines a probability model. And let me just make sure that we're in the text. You can see before we get to the classical probability. Okay, there's the probability of a simple event. Probability of an event is less than or equal to 1. probability of empty set is 0, probability of S equals 1. And this is a consequence of these three, one, and then the probability of the union of mutually exclusive subsets equals the sum of the probabilities of each of those subsets. So 3 and 4 are in some sort of are connected with each other. And so here's the idea about the what we just mentioned. Okay, so you can the probability model, there's general ones, right? And that would just be situations in which you have to specify a probability model. So one common probability model, the one that we'll use in general, or that we'll see one underlying everything, is the classical probability model, in which the classical probability model is that the probability, it's defined by probability of each simple event is the same. So P of E1 equals P of E2 equals P of E3, where these are the simple events, equals ... P of En. Okay? So in that case, just this one choice gives, and the probability model requirements this specifies probabilities for all events, for all subsets. Okay, because any event E can be viewed as, say, E1 union E3 union E7, like that, as a union of, because an event is a subset, so it has certain elements in it, so it can be viewed as that union. So the probability of E is going to equal the probability of E1 plus the probability of E3 plus the probability of E7 for this case. So you specify any event, and if you've specified the classical probability model, then you can write any probability of an event as a sum of simple ones. And since you know that the sum of these simple ones, if the size of the sample space equals n, then because they all add up to 1, you know that 1 equals n times, say, the probability of E1. So the probability of E1 equals 1 over n, where so that's equal to 1 over the sample space size. And so the probability of any event is just a sum of terms of this form. So the probability of any event in the classical probability model equals the number of elements in the event divided by the number of elements in the sample space. So this is sort of the end result for the classical probability model. And so it enables you to understand all the probability concepts in a concrete context where you know what the numbers are. You don't have to think them up or model them or whatever. Okay, so that's what we did last time, and then we did some exercises. So that's the whole sort of story that we want to tell about the normal probability. So now we just need to sort of apply that and become used to some examples of doing that. And let me